planning to do is we want to control the DC motors using pulse width modulation. So what I'm going to do today is see how we can generate a pulse width modulated signal from the ATmega 16. Okay, I want to simply generate a pulse width modulated signal from the ATmega 16. So the first step is to start the project. So we will take a new project. And we'll call it speed control. Okay, and I'm going to use the AVR ATmega 16, and I'm going to use the WinAVR. Remember, if you put AVR ASM, this means you are going to write your program in assembly. Since we are writing in C, we will use this one. Finish. So the ATmega 16, let me go and open the datasheet for the ATmega 16 and understand what is the capabilities of the ATmega 16. So I'm talking about here the ATmega 16. So you need to understand a few things. You want to generate an output on the ATmega 16. You want to use the timer counter. So first of all, where is my output? Okay, first of all, where is my output? Which output am I going to use? Which timer counter I'm going to use? Remember, we have in the ATmega 16, zoom out. In the ATmega 16, we have the timers and counters, which is two 8-bit, one 16-bit. So which of the timer counters I'm going to use? Let's assume I want to use the timer counter 0. So if I'm going to use timer counter 0, then this is my output of counter 0. If I'm going to use timer counter 1 is a 16-bit timer counter, and this 16-bit timer counter can output 2 channels. So I can have either this one, output counter B, or output counter A. I hope you can see my screen and everything is clear. Let me see here what you can see. Okay, so if you are going to use timer counter 0, then look, it's on port B. So I'm going to set port B as an output. If I'm going to use timer counter 1, then port D is an output. If I'm going to use timer counter 2, then also port D is an output. Since I plan to use timer counter 0, then I will go and use the timer counter 0 over here. This is the first step. The second step, I will go here on the left-hand side and go for the timer counter 0 with pulse width modulation. Usually in this course, let me show you. Usually in this course, when you go to the exam, I usually give you this data sheet, and this data sheet contains the information needed for timers and counters. So this is usually given to the students in the exam as an extra document. So you need to figure out how you read this document and how to use it. So the next step, I'm saying, okay, I'm using the timer counter 0. What do I want to use it for with pulse width modulation? So this is an overview for the timer counter, as you see over here. And you have some definitions: what is bottom, what is top, what is up. So bottom, the counter reaches bottom when it becomes 0, 0. Max, the counter reaches max when it reaches FF. Remember, This is a timer counter that is 8-bit, so it counts from 00 to FF, or from 0 decimal to 255 decimal. Then you have top. The counter reaches top when it becomes equal to the highest value in the count sequence. Top value can be assigned to fixed FF maximum or a value stored in OCR, depending again on the mode we are using. So the next step, you need to go and find your registers. This is all explaining how the timer operates. So here you see the modes of operation. You have the normal mode, you have the clear timer on compare match, you have the fast pulse width modulation, you have the phase correct pulse width modulation. So then you have your registers. This is the timing diagrams. Here's your registers. So we have timer counter control register 0, which is the important register over here. This timer counter control register 0, again, I'm recording in a different program. The reason I want to have the recording clear. So you will see that recording on SULMS, inshallah, later today. It will be very, very clear if you want to review this lab. Now, if you look with me, here we have the 8 bits. These 8 bits, counter select 00, counter select 01, counter select 02, wave generation mode 01, wave generation mode 02, compare match 01, compare match 00. Each microcontroller has a different registers. يعني whatever I explained in the class is not the only case. Okay, what we explained in the class, if I can open the lecture notes for timer counter, what I explained in the class, it was in here. Okay, so what I explained in the class for the timer counters, remember in class we were explaining timer counter 0 also. Here you can see that the register, it is timer counter control register 0A and timer counter control register 0B. This is for the ATmega 32. For the ATmega 16, it's a different story. So that's why this document should be with you. So if I give you in the exam a different microcontroller other than the one you saw, you need to go to the data sheet, which I will provide for you. And inside the data sheet, you need to go and search for the information. Now, if you look, the bits are, the bit number 7 is force output compare 0. Then bits 3 and 6 are the wave generation mode. So we go to the wave generation mode. Which mode are we going to generate? Is it the normal mode? So in the normal mode, you see that the top is FF and update of OCR is immediate. Timer overflow flag is max. It will just count from 0 to max, and that's it. Now, in remember the terminologies we just passed about, we just discussed them, اللي هم top والmax والbottom. Then we have the phase correct pulse width modulation, which we are going to use today. The top is FF. Update of FCR is the top. Timer overflow at the bottom. So we just need to change the top over here. Now, clear timer compare match. Clear timer compare match is basically top is the OCR, because once you reach OCR, you want to make it as top and restart from the beginning. Here, the top is FF. Remember, let me just once more whiteboard over here. Explain it once more. Just a reminder. Okay, just a reminder. The test will be on 2nd of March يوم الثلاثاء القادم بعد أسبوع من الساعة 6 المساء للساعة 7 المساء from 6 p.m. to 7 p.m. 20% module 1 and module 2. Now, remember the 3 modes of operation. In the normal mode, you count from 0 to max, from 0 to top, sorry, from 0 to top. And over here, you just keep, this is the normal mode. from 0 to max, where max is 255, and your output will be just changing when we get an overflow value on the max. So you get something like this. This is the normal mode of operation. The second mode of operation, is clear timer on compare. Clear timer on compare, you start counting. Once you reach the OCR value, OCR 0 in this case, here's your max. Once you reach your OCR value, you will stop. Once you reach your OCR value, restart from the beginning. So your timer counter will have, in this case, higher frequency. This is the CTC. That one is the normal. Now, the next one is the phase correct pulse width modulation. In the phase correct pulse width modulation, your counter counts from 0 to max, then from max down to 0, from 0 to max, from max down to 0, from 0 to max, then down back to 0. So your counter will have something like this, and over here you have your OCR. Okay, now this is max. So what happens for your output? Basically, your output will be looking something like this. This is my output signal. So I'm going to have a line going here and a line on top of here. So my changes will be happening at every instant over here. So this is what will happen. Every time you reach the OCR, something will happen. Remember, it's different modes of operation. You can clear, you can set, you can toggle. Remember the table which was in here. If I'm talking about phase correct pulse width modulation, this is the phase correct pulse width modulation. Okay, in the phase correct pulse width modulation, I can choose the toggle. I can choose to set. I can choose to reset. Depends what I want to use. Okay, depends what I want to use. The last type of signals is the fast pulse width modulation, and in the fast pulse width modulation, it's similar to the pulse width modulation, but my OCR will be somewhere around here. This is OCR, and what will happen is my signal will be changing based on OCR. It will be twice the frequency of a normal signal. So I'm going to have something like this. Depends on the value of the OCR. I can change the fast pulse width modulation. So going back over here, we are going to choose the phase correct pulse width modulation, in which the top is FF, and we update of OCR on top, and the flag is the or the flag will happen, timer overflow will happen on bottom. The clear timer correct, the top is OCR, the update of OCR is immediate, and max is the timer overflow. And the last type is the fast pulse width modulation. It is similar to the phase correct, but again it's different. So we are going to choose phase correct pulse width modulation. So the next step over here is to connect the compare output match. What am I going to do on the output? Now, am I going to toggle set or clear? Usually we toggle the output on compare match, okay? Then the compare output match for fast pulse width modulation. Again, we this is for the past. This is for the non-pulse width modulation. This is the phase correct, okay? In the phase correct here, we either reverse, okay, or we clear or we set. So over here, what we are going to do is we are going to choose to where Okay, we are going to reverse the signal over here. Then the clock, we can choose again. If you check this clock, it's different to what we studied in class. In class, what we studied, the clock, the prescalars, you see, divide by 8, 46, divide by 8, then divide by 256, divide by 8, then divide by 1024. Here's the same, but we will choose to divide by 1024 in our example. Then we have the timer counter control register 0, the output compare register, the mask, and then we have the timer counter interrupt registers. This is then the counter 0 and prescalers. So I'm going to go immediately to the program. What's happening here? Okay. So the program which we are going to use is hashtag include AVR, and let me zoom in by using the magnifier maybe, so you can see the program in a good way. Okay, hope this is clear. So then we have the integer main void. Inside the integer main void, I will start initializing my values. So DDRB is equal to 0x, sorry, this is F, 0x FF. Now, why DDRB? Remember, the timer counter control register, the output of the counter 0, OC0, is at port B, so I set port B to B0FF. Then I will initialize the timer counter. Timer counter control register 0 is equal to 0B, okay, 0B. Then I will say 0, 1, 1, 1, 0, 1, 0, 1. This is to do to set the values inside the timer counter control register. These values will be based on what we did. These values will do the wave generation mode into phase correct. Okay, the wave generation mode will be in phase correct. The compare match registers will be in reverse pulse width modulation, and the prescaler will be at 101, which is dividing by 1024. So basically, then we do the timer mask register. The timer mask register will be equal to 0x00. We are not going to do anything with the timer register. Now, all we have to do is give a value for the OCR. All we have to do is give a value for OCR 0. Okay, give a value for OCR 0. So I will start with an OCR 0. OCR 0 is equal to it's a number between 0 and 255. So let's start with 128. Okay, so basically, I can close the magnifier. Okay, so basically these lines will, without any program, see, I'm not doing any program under here. I'm just writing my program. So I will go to the circuit itself, and then I will go to timer counter 0, which is supposed to be on port B somewhere around here. OC0, this one, pin number 4. I'm going to take an oscilloscope. I'm going to take an oscilloscope, and connect port A to this one, PB4. I'm going to run my program, and hopefully without any problems. Okay, you see here I have a step. I need to just change some timings. See, this is the output. The idea is, what I did was something, I will say, very simple. I went and just wrote 3 lines. No delay, nothing. Nothing even inside the actual program. Nothing even inside the actual program. So what will happen now is, if I change OCR to, let's say, 10% duty cycle, 10% of 255 is 25. And then I go back and run my program once more. See? Now this is a duty cycle of 10%. Okay, so this is inverted. Okay, we used the inverted, so this is a 90% because this is inverted output. Okay, remember we used the inverted output, so this is 90%. If I want to do the 10%, I will go to around 220. Now this is 10%. Okay, my program closed. Hope it's clear. Do you have any questions on this? Now, what is needed from you is to write a program that will control the speed of motors using switches. So, what you are going to do, hopefully I have, this is 2 motors. It's not saved. Okay, program is not saved, but it was not that difficult. So what I want you to do is the following. You have your microcontroller. Okay, you have your microcontroller. You will connect the microcontroller to 3 switches. So these switches will basically give you different motor speed. So this is our motor connected to the driver, okay, to the H bridge. Then the H bridge is connected to the motor. Now, these switches, you connect them the way that you want. You know how to connect the switches now. Now, what I want you to do is, you will have a table of the 3 switches, 0, 0, 0, 1, 0, 0, 0, 0, and so on. And here you will have the speed. Since it is 255 divided by 8 is 256 divided by 8 is 32. So at 0, 0, 0, you will have the motors stop. At 0, 0, 1, you will run them at 32, at 32, at 8%. 8 times, you will run them 100 divided by 8. You will run them at 12.5%. At 1, this is at 1. At 2, you will run them at 25%, and so on until you reach 100% at 111. Now, yes, you can see this, but what I want you to do is connect the oscilloscope, okay, and measure the time using the oscilloscope. Measuring the time using the oscilloscope, if you come here to the oscilloscope, I will let me generate a pulse for you. Here, let's say it's pulse. Okay, I will generate a pulse here. And I will connect it to an oscilloscope. I will connect the pulse. Okay, sorry. Okay. Once I run, I will see here my oscilloscope. Of course, I can. Don't ever, by the way, don't ever close the oscilloscope from here. If you close it, you will lose it. So you stop the circuit, double click here. I just want to show you. I put the voltage on 5 and my frequency, I will put my frequency at 100 Hertz. Okay, I just want to show you how it's running. So, sorry, and then run. Now, this is my signal. How do I measure my signal and my timing? Um, there is the time measures. Where راحوا? Okay, first of all I need only source A. No, كانوا موجودين. Anyway, I will do it the old-fashioned way. I want to measure the frequency of this signal, so I will count. Keeps happening to my computer. Once more, I will take my oscilloscope. I want a pulse, and then I will connect the pulse to an oscilloscope. I will take it from here to here. I will change the settings of the pulse. Again, I will do 100 Hertz at 5 volts. Okay, and I'm going to run. Okay, so what I'm going to do, I want to measure the signal. So if I change this knob, I will change the position in the y-axis. So here you can see it is only one block multiplied by 5. I'm working with channel A, sorry, channel A. One block multiplied by 5 is 5 volts peak to peak. And if I do the frequency 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 multiplied by 1, it is 1 millisecond. 1 over 1 millisecond, it will give you 100 Hertz. So you do the same. If you want to check the duty cycle, you will need to count the time high over the time low. For the time high, it is 1, 2, 3, 4, 5. Time low is 1, 2, 3, 4, 5. But as I remember, there was one setting that we can do it. Let me check if there is another. This timer counter virtual. Anyway, it seems this one is the one available. Okay, so what you have to do is you do this, and you need to connect to the oscilloscope and show me that every time you change a switch, something will change inside this circuit. Hopefully that this is clear. I will stop the recording here, and if you have any questions, you can ask me for sure.